In this presentation and the next, we'll be studying a gantry crane example. Gantry cranes are used to move objects from one location to another, often, for example, at docks or in factories. In this example, we'll study how to adjust the velocity profile of the gantry crane so as to make the motion both quick and safe. I think you'll find, as we complete this example, that the techniques we've been developing so far in this class are very powerful, and I think also you'll be surprised at how much you've already learned and how applicable it is. Let's start by introducing some of the terminology associated with gantry cranes and describing how they function. In a gantry crane, a trolley moves across a horizontal rail called a bridge. Suspended below the trolley is the load. The trolley moves from position to position by command of an operator. As the trolley moves, the load follows below. At the end of the trolley's motion, the load may still be swinging, depending upon how the trolley is accelerated and decelerated. Let's now see what gantry crane sway looks like. Here is the version of the problem that we'll treat, and our goals as we solve the problem. We have a trolley which starts at the start position and will move through a distance of d to its final position. Suspended below the trolley is the load. The length of the line between the trolley and the load is designated L. We'd like to move it as quickly as possible from the start position to the finish position, and at the end have the smallest possible swing or no swing for the load. Our means to achieve this is to tailor the velocity profile of the trolley. Before we start to solve the problem, let's take a look at a simulation of the motion of the trolley done in MATLAB. The trolley and the load start at rest. The trolley begins to accelerate at a constant rate, then reaches a constant velocity, and then decelerates. The load is swinging in response. The trolley comes to a stop, but the load keeps swinging. A significant amount of swing remains after the trolley has stopped. Before we continue, note the velocity profile that is used during this motion. We start off at zero velocity, and then our acceleration is constant. The velocity ramps up. We reach a final velocity, and then we hold that constant for a duration. Then we decelerate with constant deceleration, hence the velocity ramps down. Finally we stop, and the velocity is zero. This is a trapezoidal velocity profile, and this profile is what we wish to engineer in order to achieve no sway. Here is the solution method that we'll follow in this and the next presentation. It consists of 6 steps. First, we'll model the system and find the transfer function of it. Then we'll define the input signal, in this case it will be acceleration, in terms of some timing parameters. Then we'll find the Laplace transform of this input signal to find it in the frequency domain. We'll then find the output signal in the frequency domain by multiplying it by the transfer function. The problem we're dealing with is zero state, so we'll only have the response to the input. Then we'll inverse Laplace transform y of s to find y of t. And in our final step, we'll pick the timing parameters so as to eliminate swing at the final position. In this presentation, we'll tackle the first 2 of these steps. We'll model the system and find its transfer function, and then we'll define the input signal, the acceleration, in terms of timing parameters. First, let's introduce our system model. The input for the problem, x of t, will be the trolley acceleration, and the output, y of t, will be the angle of the load. We'll assume that the angle is small enough that we can use the small angle approximation. Otherwise, our differential equation will be nonlinear. The differential equation for this problem will be as follows. L times y double dot plus g times y equals x, where L is the length of the line between the trolley and the load, and g is gravitational acceleration. The system starts at rest, so y at time 0 is 0, and y dot at time 0 is 0. So, we can Laplace transform the differential equation, ignore all initial conditions, and find the following relationship between the signals in the frequency domain. Y of s is equal to 1 over Ls squared plus g times x of s. So 1 over Ls squared plus g is our transfer function. Now, I've not shown you how to derive the differential equation, but you should be able to do it from what you've learned in dynamics. And here's a hint. It's a purely kinematic relationship. Now let's discuss the input, the trolley acceleration. I pointed out before that the velocity profile for the trolley was trapezoidal. It started off at 0 velocity. The velocity increased linearly due to constant acceleration until some time, which we'll label t1. It then was constant for a period until time, which we'll label t2. And then we'll have constant deceleration, so the velocity will ramp down until time 3, when the trolley has come to a stop and the velocity is 0. The acceleration profile associated with this velocity profile is as follows. During the time between 0 and t1, the acceleration will be constant, and we'll label this as a. Between times t1 and t2, the acceleration will be 0, since the velocity is constant. And during the time between t2 and t3, we have constant deceleration, which I label minus a. Now I'm assuming here that the acceleration and deceleration rates for the trolley are the same, and this is a reasonable assumption for most velocity profiles. For example, the trolley motor may set the maximum rate at which the trolley can accelerate and decelerate. It would be straightforward to treat the problem where the acceleration and deceleration rates were not the same. It would just add extra complications to the problem, and this is not needed at this time when we're just introducing these ideas. We'll now define our timing parameters for the trapezoidal velocity profile. The time between 0 and t1 will be the time of acceleration, which we label txl. The time between t1 and t2 I will label tcoast, since we're moving at constant velocity. And the time between t2 and t3 will also be txl. If the trolley decelerates at the same rate it accelerates, it will require the same amount of time to come to a stop from the maximum velocity as it did to achieve the maximum velocity. Therefore, the difference between t3 and t2 must also be txl. So with the timing parameters txl and tcoast now defined, we can write the equations relating them to the times t1, t2, and t3. t1 is clearly equal to txl. t2 will be txl plus tcoast, and t3 will be txl plus tcoast plus txl. For our problem, we want the trolley and the load to move a certain specified distance, which we label d. We now look at how this can be expressed in terms of our timing parameters. The distance traveled is the area underneath the trapezoidal velocity profile. So let's define this profile a little better. First, the maximum velocity on the profile is a times txl. The time of acceleration and deceleration are the same, and we've labeled it txl. So you note that the beginning and ending of the trapezoidal profile consist of triangles of height a times txl and width txl. The constant velocity portion of the trapezoidal profile has height a times txl and width t coast, so we can find the area here easily as well. Adding together these areas, we find the following relationship, that the distance traveled d is equal to the acceleration a times the time of acceleration txl multiplied by the quantity txl plus t coast. We will assume for this problem that the desired distance to be traveled d will be specified, as well as the acceleration and deceleration rates a. Therefore, this equation gives a constraint on the values of txl and t coast that may be used. Here are the numbers that will be used throughout our example. The length of the line between the trolley and the load, L, will be 10 meters. The distance that the trolley will travel will be 37 meters. The maximum acceleration of the trolley will be 0.5 meters per second squared. And the acceleration due to gravity, of course, is 9.8 meters per second squared. A simulation of the dynamics of the Gantry crane was written in MATLAB. This file will be available to you for you to look over. The following simulation is done with t coast equal to 10 seconds and txl equal to 5 seconds. The trolley follows the specified trapezoidal velocity profile, and the load swings in response. At the top of the simulation, you see the velocity as well as the output signal, the angle. You'll note that there's considerable swinging when the trolley has stopped. Note that the swinging is initiated right at the start of the motion, when the trolley is first accelerated. It continues throughout the constant velocity segment and seems to be exacerbated by the stopping of the trolley. So having t coast equal to 10 seconds and txl equal to 5 seconds does move the trolley 37 meters. But the problem is we have a lot of swinging at the end. So the question is there some other way to adjust t coast and txl so that we still move 37 meters but have no swing at the end of motion? It turns out there is a way to achieve this, and in our next presentation we'll show how to find the solution. We have now completed steps 1 and 2 of our solution method. In our next presentation, we'll tackle steps 3 through 6. The first thing we'll do is we'll Laplace transform x of t to find x of s. Then we'll find the response to that in the frequency domain, y of s, by multiplying that x of s by the transfer function h of s that we found in this presentation. We'll then inverse Laplace transform y of s to find y of t. And once we've done that, we'll then pick our timing parameters so as to make y of t equal to 0 at the end of the motion.